This talk has the fairly dry title of Programming Methodologies, but I hope it's interesting to you because it has two important purposes here. The first one of which is to help you select out of the multiple tracks that we have available this week, which ones are most useful to you. Many of you may already have decided. Some of you may still be on the fence, in which case I hope this allows you to either make up your mind or to spark a discussion over our lunch break with staff and decide which track is going to be of most benefit to you. The other purpose here is to give you a convincing overview of the state of the art in scientific computing and high-performance computing, and to show you that the things that we're teaching you here this week are very relevant. They're very core topics, they have extensive usefulness, and they have a long future ahead of them. They're not short-term investments. They're going to pay off for you for a long time for reasons that I'll explain in what I hope is a very compelling manner. Now, what I won't do is go over a long list of applications that really need high-performance computing, because you've already heard some very interesting ones, and you'll hear many more this week as we go through material. So I won't explain how critically important high-performance computing is to important things like climate analysis and prediction and weather prediction and whatnot. One I'll take a moment to point out, because it's interesting and we'll come back to it, is brain simulation and modeling. This is an interesting application. It's received a lot of funding by discrete efforts in different governments. It's interesting because it so happens that the human brain can be modeled in a one-to-one real-time manner right at about an exascale computing level. That's a term you've already heard and have heard discussed here, exascale computers, because we know we're all in that last step of the race that's been a decade long now to build an exascale computer. And so right when we get to exascale is about the same time we'll be able to finally model a full-size human brain, which we've grown to over the past 10 years, starting with mouse brains and rat brains and monkey brains up to human level. And so it's interesting because we'll come back to this and see how it really relates to the machines that we're building now. One thing I hope I don't have to convince you of is that serial computing isn't very interesting these days. It's unlikely that you're going to contribute to the leading edge of a lot of numerical scientific work with serial codes. Most people kind of can tell these days that serial computing, just writing standard serial codes and running it on your laptop isn't that interesting or exciting. But what you may not remember, most of you are too young to remember, that at one point in time people did kind of believe that computers were getting fast enough, Moore's law was giving us faster computers, and therefore even your serial code in 10 years is going to run 100 times faster. So serial computing still had some life in it. That hasn't been true for a long time. If we look here at a benchmark, most popular benchmark maybe out there of serial computing speeds, we can see that right around the year 2004, for reasons I'll explain, serial computers really quit getting significantly faster. Prior to that, like I said, you could sit back and have your old code just automatically run faster. And in a couple of years from now, the machines would be 2, 3, 4 times faster, and your code would run faster, and you could do new science with your old code. That's not true anymore. As a matter of fact, since 2004, we've fallen about 7 years behind the previous trend. Or in other words, machines today would be about 12 times faster than they currently are if we had continued that trend. But that trend has died. Now, it's not because of Moore's law dying. Moore's law is a term that people like to throw at anything these days that's got a nice geometrical performance improvement in science or technology in particular. But Moore's law has a very specific meaning. Gordon Moore in the mid-60s observed that transistors seem to be increasing at a density, a doubling in their density about every 18 months to 2 years. And he predicted that this would continue for a while. What's astounding is that a prediction made by a bright guy in the mid-60s has remained true over 50 years, despite multiple complete changes in fabrication technology. The engineers to keep this going have done heroic efforts. As a matter of fact, about 20 years ago, people started predicting Moore's law is going to end. It's come to its end because we were running up against the laws of physics in some sense. The wavelengths of light we were using to make the chips, how many atoms across transistors are. And so about 20 years ago, we started to predict the death of Moore's law, and people have been predicting it pretty consistently for the past 20 years. Looks like they're finally maybe about right, but not quite yet. But finally, Moore's law really is coming to its end. We really are running up against the fundamental laws of physics, but it hasn't happened yet. That's not the reason serial computing is dead and parallel computing has taken off. Intel has continued to shrink things down. This is Intel in particular, but now they are having problems. For any of you that pay attention to these kind of things, you'll notice that they're having a hard time getting to 7 nanometers. And the other people that have gotten to 7 nanometers, Samsung and TSMC, are more or less changing the definitions. so they can say they got there. As a matter of fact, a whole lot of this stuff these days is more marketing than it is engineering. It's kind of sad. I have a number of slides in the appendix to this talk for those of you that are interested in that kind of stuff. If you go to the appendix, these talks are on the Moodle. So if you go to the appendix, there's all kinds of stuff there showing how the technology, the electronic level is really running up against walls. I find it to be an interesting point for discussion, and we can have those discussions offline. But suffice it to say that so far, the engineers have been able to give us the transistors. Modern computer chips are much more sophisticated than the ones from 5 years ago. They have a lot more transistors. They have a lot more going on in them. So Moore's Law isn't dead yet. Moore's laws continue to give us all these transistors. So why is serial computing dead? And maybe more to the point for you, why are you being forced to learn all this parallel computing stuff that we're teaching here this week, right? Why can't we just write serial codes and the chips can just figure out how to run them faster? Well, this is the reason right here. This is maybe one of the least exciting looking slides, but maybe the most important slide you'll see all week if you really want to say you understand modern computer design. And more importantly, if you want to say you understand which way it's going, what's the future of computing? It's all explained right here on this slide, as boring as it is. On this side here, we have those clock rates that I showed you when I said they stopped increasing in around 2004. These are clock rates for a variety of different chips here. And we can see that, yes, indeed, around 2004, the clock rates quit going up. Anybody that was around in computing before 2004 can clearly remember when the big competition was in clock rates, the megahertz wars, they called it in the 90s. How much faster is my chip than yours? And you can remember when it went from 300 megahertz to 600 megahertz in a couple of years. And that was exciting. You'd buy the faster chip because clearly a faster clock rate's faster and more powerful. Now, any chip you buy is a couple gigahertz plus or minus. It's been that way for 10 years. This is what we can see here on the right. But that's not exciting and that's not news. What is interesting here is this graph on the left, which seems kind of boring. It's showing how many watts per square centimeter a modern chip dissipates in terms of heat versus years here as we go along. And this graph should impress you because if you actually look at the units here, they're perfectly comprehensible. Modern chips are generating about 100 watts per square centimeter when they're running full out. 100 watts is an awful lot of power, right? A 100-watt light bulb is a very hot incandescent light bulb. You wouldn't want to put your hand on it. You'd burn yourself immediately. That's how much power a modern computer chip is dissipating when it's running at full speed in a square centimeter, a small little area. It's amazing these chips don't melt themselves down already, but you can understand why the engineers can't keep pushing the clock rates up. It makes them run hotter. They're already on the verge of melting. This is the #1 design issue in modern computers. That the engineers keep giving us more transistors. They can cram them into a smaller area, but the chips will melt if we run them any hotter. This is the dominant theme in designing modern computers, is keeping them from melting. Now, this is not a new thing. Oh, by the way, before I leave the slide, I'll point out here, just to put it in perspective, modern chips run much hotter than a hot plate. A hot plate doesn't put out 100 watts per square centimeter, not even close. So you're running a modern computer hotter than a hot plate. And many of you can maybe sense that. You know your laptop gets a little warm in your lap when you're using it on the airplane. Your cell phone may get a little warm when you're using it. You can sense heat dissipation is a big issue in modern computers, certainly inside the computer. Now, this is not a new issue. Here's a picture of a Cray computer from the mid-'80s, and that tower in front of it, those tubes, which when it's running bubble away like a fountain, it looked very decorative when it was running, was because of the liquid cooling. So keeping the machines from melting is an old problem in computing. We used to solve it with very fancy, sophisticated, exotic liquid cooling technologies and computers like this one. Then we decided that that wasn't really practical. So modern machines we build now are mostly air-cooled. They do have some liquid cooling in them. But at any rate, the problem we're struggling with is keeping the chips from melting. So what have the engineers come up with a solution? This is the solution they came up with. This is why you're all here this week. Is the solution the engineers came up with is if we can't run one chip really hot because it's going to melt, well, we can run 2 chips a little bit slower and get more performance for the same number of transistors. So the math is right here. If we take and reduce our voltage or our clock speed by about 15%, then we get a little bit less computing out of a chip. But we drop the power dissipation a lot. So we can run 2 of these chips now with the same amount of power, and we get about 1.8 times the performance. That's the math of modern computing. It's the math of your cell phone. It's why it has multiple cores in it. It's the math of these big machines we build with millions of cores. Is to keep them from melting, we use multiple cores instead of one core running really fast. And you can see this in any modern computer chip. Here are some standard processors. This is nothing exotic or, these are the things you find in your laptops. This is the processor. This last one, Skylake, is the processor we're going to use for our workshop this week on bridges. If we look at processors these days, they do almost everything in parallel. Around the turn of the century, a Pentium chip got 3 floating point operations for every clock tick. And we thought that was pretty nifty. That's, hey, you're getting 3 operations per clock tick. That's a little bit of engineering. Today, a Skylake processor gets 2,700 floating point operations per clock tick if you're using all of its parallel capability. In other words, if you're not a parallel programmer and you're using a modern processor like a Skylake Intel processor, again, a standard desktop type processor, if you're not using it in parallel, you're wasting almost all of its capability. Somebody that is not a parallel programmer cannot use any modern hardware effectively. This is the moral, this is the theme of modern computing. And you can see here, there's multiple ways that it involves to get these 2,700 flops. It's got a lot of cores in it. It's got vector instructions. These are all things we'll dive into in our tracks this week in the classes we're going to do. But the bottom line is, if you use this thing in serial mode, you're not using a fraction of a percent of its hardware capability. So that's why parallel computing is incredibly important just to the desktop level, to the cell phone level, if you want to be a good programmer. So if we put all these things together in one graph, it looks like this. Moore's law keeps giving us these transistors, so we've got the transistors, but the serial performance hasn't gone up much. It's kind of plateaued. That's because the clock rates have plateaued, and that's because the power dissipation has hit the level where things are going to melt. And so how do we keep the performance going up? It's these black dots here. We increase the number of cores that we have in the processor. So things have gone parallel as an end run around the laws of physics that want to melt our modern electronics down. This is the theme of all modern computing. Scientific computing on the high end, it's very obvious. But anybody designing, again, a cell phone these days has to worry about this kind of stuff. So the way this is very visible in a massively parallel machine like the ones we've been talking about, you've been hearing about today, is you can see we cram in racks as dense as we can. We cram in these fancy processors that have all these vector parallelizations and things going on. We stick a bunch of these processors together. We connect them with networks. And we build big machines that have millions of cores these days. So it's very obvious and visible what these machines look like. You can tell they're very parallel. What does it look like from the programming perspective? Because that's what you care about. That's what we care about this week. Well, we look at it from parallelism in a programmer's point of view. There's a lot of levels. There's a lot of stuff that goes on. And which ones do you care about? Which ones do you have to know how to use? A lot of the stuff is low level, and you hope that the compiler writers and the engineers get together and fix it so you don't have to worry about it. So you can write a kind of serial-looking code, and the compiler can take advantage of stuff. And that's largely true for the vector instructions, which we'll talk about in classes in a little bit more detail, and a lot of the other stuff that goes on behind the scenes. Some of this stuff, by the way, is responsible for these meltdown and Spectre security flaws that cause great concern you may have heard about. Well, that's because all the tricks that they do at this low level to make things work efficiently in parallel come with great complexity and now apparently great security risk. So that's these things right here, these speculative execution and whatnot. But at any rate, you hope that all this stuff is taken care of by the compiler. You hope that that's not your problem. It's not always true, and it's helpful to be knowledgeable somewhat because you can sometimes help the compiler to great effect. But by and large, you hope that that's the compiler's issue. On the other hand, as soon as we start talking about using all the cores on a chip, and all modern chips have a lot of cores. You can't buy a single core chip anymore for anything, not even as a cell phone. All the modern chips that have multiple cores expect you to be responsible for that. The compiler can't really do that for you. And that's where OpenMP comes in. And you'll have the opportunity to learn that this week. Now you'll also find, and I'll talk a little bit more about it, that GPUs have become a big part of the mix. And we'll see exactly how they fit in the picture. But that's up to you as a programmer to do explicitly yourself, as with CUDA or OpenACC, something like that. And lastly, if you want to put a lot of these pieces together, stick them in a bunch of cabinets and stick a bunch of cabinets in a data center, then that's MPI. And that's up to you to figure out how to do that as well. So the compiler is only responsible for the lowest level stuff. Everything else is up to you. And fortunately, you came to the right place to learn that. Now, a couple things we won't talk about, but they're also important, is there are other chip-type architectures that are either custom chips, ASICs, or field programmable gate arrays, digital signal processors. These are all types of parallel computing, and some of the things you're going to learn here this week apply actually pretty directly to them as well. We just won't have the time to talk about them. But for certain people in different areas, they're very, very important ways of doing parallel computing. We also probably won't talk a whole lot about, well, we will talk. You'll hear us talk about parallel I/O this week, and that's a good thing. Because I/O sounds boring until you actually start doing science, in which case it becomes really important to read data in and write data out. And if you've got a successful parallel code running successfully in a parallel machine, it's going to consume a lot of data and or write an awful lot of data. So you can't overlook the importance of good parallel I/O. Those are all important aspects. But let's take a quick walk through an application and see how all these different pieces can enable an application run in parallel. I like to pick a weather model because everybody understands what we're trying to do here. It's also got a long history, as we'll see. A weather model like you might have written in 1970 if you were writing a Fortran code for the National Weather Service to predict the weather forecast for the next day would have basically taken a big grid of the area, in this case the United States. We take the United States, break it up into a big grid, and then your serial code would just go over this grid and apply the numerical equations that solve for the weather, that involve all the variables like wind velocity and barometric pressure and humidity and whatnot. And that was your serial code, and that was the best you could do. Well, a guy named Richardson, back in 1917, figured out maybe a better way to do this in parallel. Richardson decided that if we took and locked 64,000 meteorologists in a big room, each one of them could be responsible for a little patch of ground, and they could calculate the weather on their little patch of ground, and the only thing that they would need to know as an input is the information from their immediate neighbors to the north, south, east, and west. Because your immediate neighbors give you all the information you need to know to calculate your weather a little bit forward in time. So your neighbors tell you, you and your neighbors exchange this information, and you calculate your weather forward an hour, and then you do the calculation over again, and you can kind of march forward in time and do your weather prediction. So you might say, why is Richardson doing this in 1917? Because clearly we know that you can't calculate weather with pen and paper or even mechanical computers, but that was his idea. So as much as we might find it naive because we know we need a lot more computing power, the idea is very sound, and it's exactly what we do today. So if you're an OpenMP programmer, the way you attack a weather model like this is you break the weather map up into small patches, maybe for 4 cores, you'd break it up into 4 patches like this, and each core works on its own quarter of the map. And whenever it needs some data from the neighbor, it just looks over at the neighbor's part of the map and figures out whatever data it needs on the border to calculate its own weather. And we might speed the application up by a factor of 4 with OpenMP on a 4-core machine. That's exactly how this would work. So it's like 4 meteorologists in a room and they're all working on the same map. And you program this with something like OpenMP, which you'll have the opportunity to learn this week. Now, you also have heard about the great successes of GPUs in computing. You've seen examples of it, talking about machines that are being built here. GPUs are very, very good at lots of types of calculations, a little bit simple-minded about other types of calculations. So they're not as smart as normal cores, but they have an awful lot of cores, and a modern GPU has many thousands of cores in it, might have 4,000 or 5,000 cores in it. So with a GPU, we take our weather map, and instead of trying to calculate it on our cores, we send it across the PCI bus, the bus that connects the card up, into the GPU, and the GPU has thousands of cores, and it works on that map, and it works much faster because it's got all these thousands of cores, so you expect it to run faster than your CPU, and it does what calculations it can, and then it gives it back to the CPU so that it can output the data or do other things that the CPU has to do. This is how GPUs compute. So this is like having one meteorologist, because the GPU is pretty dumb and inflexible, but the GPU represents having thousands of people that can do math. They don't know anything about the weather. They can only do a limited number of things, but if you tell them exactly what to do, you've got an army of them to work on it. So that's the way that GPUs work on a weather problem, and that's what we're going to talk about this week. You could do it with CUDA. We're going to use the much, much easier way of doing it with OpenACC. It's a much advanced method over CUDA. The last way that you can attack this map, if you really don't have enough computing power with whatever fancy workstation you build, no matter how many GPUs you cram into it, is you need to expand up. You need to have lots of cabinets now with lots of computing resources. You need one of these supercomputers, and anytime you need something that's more than a single node that's got to connect over a network to another node to break a problem up, now we're talking about MPI. You really don't have any other practical option. So MPI gives us the ability now to spread this map out as much as we want and break it up into as many fine pieces as we want. So we distribute it, and we might have one computer working on each state, for example. That wouldn't be the smartest way to do it, but it would work. And MPI allows us to do that kind of thing. So that allows us to get as many meteorologists as we want involved in the problem, at the expense of it being a lot more complicated to send all this data around now, because you can't just look at the neighbor's data. They've got to explicitly send it back and forth, as any MPI programmer knows. And that's MPI, and that's what we'll be talking about this week. So these pieces fit together like this. Any modern machine, you've got, say, in this case, a 6-core processor with some memory. Well, that's OpenMP. If you want to stick a GPU in it to get a lot more math capability, a lot more flops, that's where OpenACC comes in there. Now, that's not enough for you, and for many of you, that's not. That's why we're here. We're interested in using leading-edge resources. When you need more than one workstation, then you're leaping into the world of MPI, and that connects as many nodes as you can, well, afford together. That's how that works. And if we look at modern machines, that's exactly what they look like. Here's a list of the world's fastest machines. You've heard about people ranking in the top 500.org list. Here's the latest release from June of the top 500.org list. And if you look at these machines, you can see that they all have, well, millions of cores is becoming a thing now. And most of them have accelerators of one sort or another. NVIDIA GPU is the most common in the list, but you also have Intel PHYs. And some of them have even, and you've heard about one here, the next machine that's going to be built here is going to have its own custom vector kind of processors in it to emulate what a GPU does. That's already true for the Chinese machine. It was #1 for a nice stretch there for about 3 years. It uses OpenACC as the only way actually to program it. It doesn't have a GPU, but it uses GPU type programming in its vector processors, similar to what you were hearing about here. So these are the 3 programming models we're going to cover this week. And they cover all of the bases on programming modern hardware from cell phone all the way up to supercomputers. And at the supercomputer level, they're really the only significantly useful ways to program these machines. Now, there are some other ways out there to program these. There are other paradigms. There's data parallel. Any of you that are Fortran 90 programmers, and Fortran 90 is now so old, I hope any Fortran programmers using at least Fortran 90 parallel data statements, data parallel type statements. If any of you are using that, you're automatically using another way of doing parallel programming, data parallel. So data parallel is another way that we're not going to get into explicitly this week, but if you're a Fortran programmer, it just kind of naturally happens in your code at times. It's wonderful if it does. It's limited in what it can do in terms of complex geometries. PGAS languages are fancier extensions to languages to try to do things that aren't as complicated as MPI, but still scale really well. They've been around for a while. They haven't gained a lot of traction, so I can't say they're significant, but they're interesting, and everybody's hoping that there'll be a solution because MPI is so tough to do. But they've now been built into Fortran. As a matter of fact, if you're a Fortran programmer using the Fortran 2008 standard, what used to be called co-array Fortran is now part of the language. And there are frameworks and other things that attempt to enable parallel programming. But the bottom line is today, petaflops computing, so a petaflop being 10 to the 15th operations per second, floating point operations per second, has caught on everywhere. There are lots of these big machines out there, lots of them, hundreds of them now. 500 machines are petaflop or better. So you have lots of resources if you can parallel program them. And if you can't parallel program, you can't use those resources effectively. You've heard about exascale machines and the race to get to exaflops. And this is, right now, this is the reason we're fixated on that is because for the past 10 years, we've had this graph kind of growing in front of us. This is that top 500 list, and this is showing the fastest machine on that top 500 list here. And we can see that it seems to be headed towards an exaflop right here, right around 2020. We've been staring at this list for 10 years. So about 10 years ago, the race was on. Who's going to build the first exascale machine that could do 10 to the 18th, a quadrillion floating point operations per second? So we've been in this race for a long time. We're getting near the finish line right now, and it's getting exciting. And you've heard about a number of machines here that hope to be significant on this list. But you can also see there's some real plateaus recently. This graph is not inevitable. It hasn't been a smooth climb, and there have been some real plateaus in recent years. This is the end of Moore's Law, is hurting us a little bit here, but we still keep lurching ahead. One of these bumps here, the thing that kept us on track, was adding GPUs and accelerators. So if we look at how we're fighting our way, in spite of Moore's Law letting us down, how we're fighting our way to exascale, we can see there are a couple of quantum leaps that are important. GPUs are the first one that's already happened and was very important. Without GPUs contributing their flops, that graph would have fallen off a long time ago. We wouldn't have gotten to exascale. The second one's happening right now, and that is 3D electronics, vertically integrated electronics. It's a critical part of keeping us on track. Again, in spite of Moore's Law letting us down, lots of commodity electronics, cell phones and whatnot, are now using vertically integrated stacked 3D electronics. That's a huge thing because it buys us a performance advantage that Moore's Law isn't giving us. It aggravates that heat problem I talked about, so it's an interesting trade-off for engineers, but it is buying us some performance. And so right now, leading-edge electronics are going 3D. They're going into 3D packaging, and it's very interesting, and it's the only thing that's kept us on track. We hope there's another boost coming soon, and that's silicon photonics here, which is switching a lot more to optics, fiber optic type connections instead of copper connections, but also taking that down to the chip level. That'll be very important because moving data around on these big machines takes much more energy now than doing the actual calculations. And so coming up with more efficient ways to move the data. And this is now starting to be deployed as we speak. So these are important quantum leaps. Now there's also, people will make the contention that we really need alternatives to Moore's Law, to modern electronics, which are subject to Moore's Law. And so instead of what we are today, which is CMOS or silicon-based electronics, that are packaged like the same way we've been building computers for 60 years. The modern computer, has its registers and its memory, and you move things back and forth. Well, maybe we need to do things a little bit differently. Maybe we have no choice. One thing we can do is move beyond silicon electronics, beyond CMOS, and there are a number of interesting alternatives. So you can talk about things like graphene-based electronics, planar graphene electronics, and alternatives to silicon, even some older technologies like gallium arsenide and whatnot. Maybe that's one way to go, and there's a lot of interest and investment being made there. Maybe we throw away the classic computer architecture and do something radically different. Quantum computing is a good example, maybe the most prominent one of that. A lot of discussion and interest and excitement in quantum computing. There's some reason to be pessimistic, but there's some reasons to be optimistic. The more you understand about quantum computing, the more confused you get, because the two are, the reasons for pessimism and the reasons for optimism are both valid. It's rare that you see a technological field where the absolute leading edge experts disagree so much on how soon it's going to be deployed. You will hear people make the contention that quantum computers are a couple of years away from being able to do interesting things, and you will hear other equally informed experts say that they are decades away from being useful. And it's very interesting. I encourage you to explore the subject if you're interested in that. It's more accessible than you might think. And a different approach that says we're going to keep the silicon electronics, as we know what we're doing there. We've got a lot of knowledge built up there, but let's go with a different architecture. Let's go with something that's wired differently than our Harvard computers, which is the kind of computer architecture we've been using for 60 years, and neuromorphic computers, where we start to wire things up like actual neural nets at the electronic level, are an example of that. So we've got a lot of approaches here. And if we have to go to something different, it won't be the first time. We keep thinking that computers look the way they do because we've been stuck at this integrated circuit level for a long time. But before integrated circuits, there were discrete transistors wired together. Then there were vacuum tubes, the first computers that were probably interesting. There were electromechanical relay computers, and before that there were completely mechanical or mostly mechanical things like Hollow Earth card readers. So if we get forced out of electronic integrated circuits, it won't be that traumatic. So I want to conclude talking about hardware, though, with circling back to that brain simulation I talked about. I said that we're going to be able, with an exascale computer, to be able to run a brain simulation on one of these big machines. It'll take 20 megawatts, maybe more. We just heard 40 megawatts in the new facility being built here, right? That's a ridiculous amount of power to be able to simulate a human brain, which actually runs on your brain on about 20 watts. So it tells you there's a lot of room for improvement. So there's an awful lot of cleverness that we've yet to wring out of the way we build these machines. So here to summarize it, the future of computing and where you fit and where this week's agenda fits is that everybody's roadmap for these big machines, and I've already seen it on a few slides here, has a term MPI plus X. MPI plus X is a shorthand for saying whatever the machine you're going to build in the next 5 years, you better make it so you can program with MPI, because that's the only guaranteed way to scale up codes across a bunch of nodes. But you'd also like to be able to effectively use the parallelization on those nodes, be they GPUs or multiple cores, and that's some other, the plus X is usually something like OpenMP or CUDA or OpenACC. It almost always is. But that is everybody's roadmap for the indefinite future. That's all the machines being built now and being funded to be built in the next couple of years. There are alternatives that are interesting to talk about for computer scientists, like these PGAS languages. There are languages like X10 and Chapel that are people or functional programming languages computer scientists love. None of these have gained any traction in real applications. All the big applications running these big machines currently are MPI plus X. But these are interesting topics for conversation. What about big data and deep learning? Where do they fit in this puzzle here? Well, they have their own kind of separate role off to the side in the way you program them and the way they use hardware. So fortunately for you, this time around, we're going to have the attention and the time we're going to devote to talking about them as the separate topics they deserve. So we'll talk about big data on Friday and how it fits into this picture, and we'll talk about deep learning on Thursday and how it fits the picture. And you'll be really well positioned to appreciate how those work, because between now and then, you'll be thinking about parallel computing, which is what enables these. Big data and deep learning only exist because of parallel computing. And we'll really be able to talk about them in substantial, deep, profound ways, because we'll be able to talk to parallel programmers. So that's Thursday and Friday. But again, this is the way things fit together, is you program CPUs with OpenMP, you program GPUs with something like OpenACC, and if you want more than one of them, if you need more than one of them, you better be using MPI. And the last remark I'll make is that we have a hybrid challenge to see how well you can weld these things together. I won't go into great detail with it now. We'll both, whether we take the classic track or the OpenACC track, at the end of that track, we'll introduce you to all the details of this challenge. It's been a lot of fun over the past 4 or 5 years that we've run this challenge here, because it will challenge you to form teams potentially, if you'd like, and to combine the knowledge that you've learned about GPU programming, about multi-threaded programming, and about MPI programming to run a particular test problem. It's a nice scientific application to run that problem as quickly as possible. So that the winner will be, and you'll get your trophy, the winner will be the team and or individual that comes up with the best solution. It's always a fun thing that we kind of run in the background here. And again, we can go into details. As a matter of fact, for any of you that are really excited about it, beforehand, we can even, Ludovic, where are you out there? Can you stand up? Stand up, introduce. Ludwig will be coordinating the hybrid challenge, and so he's the person that we'll all refer to with questions and everything else. Once it gets started, there will be a flurry of questions and lots of activity and excitement. But between now and the official launch of the competition, if you have questions about it, we can start to answer them in advance. Okay, with that, I hope I've given you enough information to try to decide which track to do. Please seek us and other staff out between now and the start of the classic track and the OpenMP track, OpenACC track this afternoon. If you have questions, we can help guide you in the right direction. And we're almost on. You have a couple of remarks. Armand has a couple of remarks, and then Scott, I think you have a couple of remarks. So a couple quick remarks, and then we're almost on schedule.
Yeah. Thanks a lot, John. Okay.